Hey everybody, we're almost done. In this video, we're going to do when the divergence of a vector field is 0. So the del operator dotted with F when it equals 0. If F was a velocity field of a fluid, then the divergence of the vector field represents the net rate of change over time of the mass of the fluid flowing through the point. I say from the point, but through the point is better. And it's per unit volume. So we've got mass per unit volume. This is density. So that's what divergence is showing. So if there is no change in the density because the divergence of the vector field is 0, it means the density is not changing, and we call that incompressible. There's a lot of studies with incompressible fluids that you'll see in physics and beyond. You got a lot of, if you're going into math, physics, or applied mathematics, you've got some very interesting stuff in your future. It's really great. I envy that you get to go down this rabbit hole again, or go down this rabbit hole for the first time. But let's do another version where we're not just talking about incompressible fluids. Let's say the divergence of some vector field G equals 0. But we know G is the curl of another vector field F. So what we've got is the divergence of the curl of F. Divergence of curl of F. And it equals 0. Is this an unusual thing? Let's just write out what the divergence of the curl of F looks like. We've got the ddx, ddy, ddz for our del operator. I wrote this down earlier as the curl of F. You can rewrite out curl of F if you need to come up with these components, but that's what they are. When we apply the dot product to them, ddx on each of these, I wrote it in notation that a lot of textbooks and stuff use. So I did not write in the easier to read one. We've got the second derivative of h with respect to y, then x, minus the second derivative of g with respect to z, then x. That's the I component, or was the I component. It's no longer a vector because it's the dot product. You go through and do each of these, and you're going to get these values here. So second derivative f with respect to y and z, minus the second derivative h with respect to y and x, and then second derivative g with respect to z and x, minus the second derivative f with respect to z and y. Remember, with Clairaut's theorem, these were interchangeable. So like these two are the same value. One is positive, one is negative. They zero out. The green ones, I've got G is X and Z. The one on the left is negative. The one on the right is positive. They zero out. And then with respect to F, it's Y and Z. The one on the left is positive. The one on the right is negative. Those zero out. So the divergence of the curl of a vector field F is 0 all the time. This is not unusual. That is a rule. Divergence of the curl is 0. Let's look at an example where we can show something could not be the curl of another, where we show one vector cannot be the curl of another vector. So we have our f is xz, xyz, negative y squared. We've used this in a couple of videos. This cannot be the curl of another vector field, which means f is not the del curled with or crossed with g. How do I know? If we take the dot product of f, it is non-zero. But if f was a cross product of the del operator and g, we would have this, the dot product of a curl, or divergence of a curl is always 0, which means we have a contradiction. If f is this, we get 0, but f doesn't give us 0, so it can't be it. We got one more video coming up. I'm going to wrap up all the equations. Some of the stuff I haven't covered in videos, but it is what it is. Peace.